translation and mutation. In translation and mutation, we're going to take that RNA transcript that we made and put through processing, and the worker is going to read it and build it. The worker that does that is the ribosome. And it does that by reading the letters of the DNA, or sorry, RNA at this point, every 3 letters. So if we had ATG to start with in the DNA, in the RNA, that's going to be AUG. And that AUG is then the codon that is interpreted by the ribosome. And so we get AUG, it's going to code for methionine. That's an amino acid. The codon tells us which amino acid needs to be put into the protein that the ribosome is building. So AUG codes for met, and it adds that amino acid, then adds the next amino acid. But it doesn't work by having the ribosome actually read it. It's all chemical reactions. And so what's happening is the codon is actually met by a anticodon. And the anticodon is found on a different type of RNA called tRNA. tRNA is like Uber for amino acids. And the way that the Uber knows it's gotten to the right place is it's going to have a 3-letter code on it that is the complement of the codon. So if it's AUG is the codon, the tRNA will have on it UAC, the complement to AUG. UAC tRNA will only ever pick up methionine. And that is what allows for that chemistry to make sure that we get the right amino acid for the codon. Now, I want you to understand that's how it works, how the codons and anticodons work together to get the right amino acid there. But when you're interpreting a strand of RNA, all you need to worry about is 3 letters at a time. What is the codon? The codon is what this chart is used to tell you what amino acid goes in there. Go ahead, Austin.
So you use the tRNA to get, like, so you use the U, for example, you use the first column, then you use the 3rd row for the A, and then it's like C means the 3rd one down would be the idea. Like, so that's how you got ACA.
Yeah. So really quick, just the tRNA, we want to ignore that when we're interpreting this chart.
Okay.
This is going to be just the mRNA, the RNA that we built in transcription. That's what we're going to use this chart to interpret. So yeah, the left side rows are going to be the first letter. So if our first letter is C, we would switch to this second set of the second row of codons here. If our second letter in our codon was U, then we would know we're in the first column. And then the 3rd side over here would give us like CUC. Oh, now I know that's my codon, and that's the leucine.
That makes sense.
Yeah, okay, good. All right. And so if we were interpreting this strand of DNA here, AUG, that's our codon. We come up here. Met is our first amino acid. That's what we put in. Our next one, CAC, CAC, that's a histamine. So that's what we put in next. So that's how we interpret it. Yeah. Okay, let's talk about mutation. Okay, and we'll hopefully be able to use our example here. So let's say our correct codon is UGU. Well, in DNA, that's actually TGT. And the mutations that we care about are actually happening in the DNA, right? So TGT is what we would be working with. So our DNA would be TGT, then that would become our RNA, which would be UGU, because it replaces T's with U's. And then we would read our code, UGU, codes for cysteine. Well, what would happen if in the DNA that was mutated, instead of being TGT, it became TGC? If that happened, our RNA would then be changed to UGC, and UGC would result in the same amino acid being coded for. That mutation then would result in no change at all in the protein. Because of that, we give it the name silent mutation. Because yes, it did mutate from a T to a C, but it resulted in the exact same thing being produced. So that's a silent mutation. If instead we had a mutation from TGT to TGG, now we go to UGG instead of UGT, sorry, UGU. That's going to result in a different amino acid, tryptophan here. That different amino acid is going to result in a change in our protein. And the order that those amino acids are linked together determine the shape that that protein takes. And if that protein takes the wrong shape, it will result in something not being able to do its job. For example, when we talked about enzymes, right? Enzymes help those chemical reactions happen. Enzymes only work on specific things. They're substrate specific. If their shape is off, they won't be able to grab a hold of the things that it needs to, and it won't be able to do its job. So a mutation from a cysteine to a tryptophan, and I don't know if this is the case, but if this were a hydrophobic amino acid and this were a hydrophilic amino acid, that's going to result in a big shift in how that protein forms in your cells. That is what we call a missense mutation. So we had a silent mutation when there was no difference. When we change from one amino acid to another, we have a mistake. That's a missense mutation. The last type of mutation in this section that we're going to talk about is, okay, we start with TGT. What if instead it went to become a TGA? If that was the mutation. That would give us, instead of UGU, UGA. UGA codes for stop. Now, a stop is not an amino acid. A stop just means the whole process shuts down. Met, that's going to be an amino acid. If it's a stop, the process just is done. Okay, no amino acid gets added. Think about what that means. If this were our third amino acid in our chain of 1,000 to form our protein, if it was a missense mutation, we'd have that one amino acid messed up and the rest would all be correct. So we might be able to get by with it functioning if they were both hydrophobic amino acids, for example. It may operate mostly the same. If it were a stop mutation, or sorry, a stop codon that we mutated to, now all of a sudden we're only going to have 3 amino acids, and all the rest of those will never be added to our chain. That's going to have a profound impact on the protein that's made. So this one, because it gets a stop, we get no more amino acids added. So no more amino acids. We're going to call this a nonsense mutation because there's nothing else added to it. So silent mutation, we get the same amino acid after the change. Missense mutation, we get a different amino acid after the change. And nonsense mutation, we get a stop after the change. The last set of mutations that you'll need to know is called frame shift mutations. So if we were to have our chain here, right, AUG, CAC, UCU, and we went along, we would be having those amino acids read every 3 letters. A frame shift mutation happens when we have an insertion or deletion. If we were to add an extra C in between that G and C here, now all of a sudden, our reading frame shifts. Instead of being CAC, we have to shift it to the left because we have an extra base in there. And that's going to cause the reading frame to shift for every amino acid after, or for every codon after. And that means that every amino acid is potentially different after that point. So that's if we add a letter. If we subtract a letter, if we pulled this C out, the same thing would happen just in the other direction. We'd have a different reading frame for our codons. So those are frame shift mutations. Those are pretty impactful on how well the protein gets made, obviously. All right. Any questions on translation and mutation?
I had a quick question. So I watched that video right there at number 15, And it kind of alluded to there being certain connections between like letters. Like it'd be like, oh, we know that A is matches C or is across from C. And that was like a part of I think it was like just the normal DNA sequence. Like, how you I don't know how to describe it. You know how you like go across and some of the letters go from like U to T or whatever. So is there like any other rules that are important to know? Is, I guess, my roundabout way of asking. I know that.
Go ahead.
Go ahead. No. I mean, I was just wondering, like, are there any other rules? Because I know that like T turns to U in certain cases, but are there any other like set rules like that?
In DNA, A will always be across from T, and G will always be across from C. When we go from DNA to RNA, when we go through transcription, the T will be replaced by a U, but the G on so if that's all we really need to understand, I think, from that is that.
Okay, that makes sense.
Yeah. So in DNA, the A's and T's pair together, the G's and C's pair together, but RNA is going to operate a little bit differently. Now the codons, if it's AUG, A instead of pairing with T will pair with U, and G and C will be the same. If you're doing the codon and the anticodon pairing up.
Okay. Yeah. That does clear it up. Thank you.
When I was first learning this, I was fresh off my mission. And for some reason, this analogy just made sense in my head. And I'm going to just preface it by saying Joseph Smith was a ribosome. So think about this, right? What is the job of the ribosome? Well, it's going to take RNA and translate it, because that's where we use the term translation, right, into an amino acid. That's what Joseph Smith did with the Book of Mormon, right? Well, there was this whole other thing that happened before that. When we talked about transcription in our previous lesson, we had all the DNA code, your whole genome. That's like the Nephite records, right? And well, what did Mormon do? Well, Mormon took the important parts and he transcribed them. He only copied down the important parts into the gold plates. So the DNA is like your whole genome. That's all the Nephite records. And then the job that Mormon did was like the RNA polymerase. He transcribed it into just the important parts. So, if that analogy helps you, great.
That's a good analogy.